In this video, we're going to be completing our reference sheet for transformations. If you don't remember a transformations affect the appearance of apparent functions, and there are two main types, and that's rigid and non-rigid. Rigid changes the position or orientation. It moves it up or down, left or right, or it might spin it. Translations and reflections are rigid transformations. Non-rigid distorts the shape of the function by changing its size. And that would be like a dilation. And we're going to be going over all of these in this video. And as it says here, it is so important to memorize these rules. These are very important. We're going to be using them for the rest of the year in this class. So make sure that we understand them. Now, I'm going to be giving an example of each of these from a parent function and how we can perform each of these using Desmos. Okay, let's start with translations. And again, a translation is a shift. So how do we shift? First off, how do we shift a function up or down? And let's go back to Desmos. If you have a function like y equals x squared is our parent function here, anytime you add or subtract, now here's what's important. It can't be to the x value. Anytime you add or subtract a number to the end of a function, over here where it says plus 3, if we add 3, it goes up 3. If we add 2, it goes up 2. If we subtract 1, it goes down 1. It's the identical function. It's just been shifted up or down. So that's when we subtract from the end of a function. So to move a function up or down, we will take the entire function, the whole f of x, and we'll subtract a value, or we'll take the entire function to move it up and we will add a value. So f of x minus k or f of x plus k. Now, how do we move a function left or right? Notice that in the previous example, we subtracted and added to the end of the function. If we move it left or right, the transformation is applied directly to the x value. And always remember this, because the x-axis is a horizontal, the left and right axis. So anytime we want to move a function left or right, the application of the plus or minus will be straight to the x value itself. And here you see an example of that. Your original function, y equals x squared. Now again, notice where the minus 3 is located. Inside of this function with the x. So the whole function is the stuff squared. Now we have, instead of just plain stuff squared, we have x minus 3. Now something else special about what happens when we do the minus 3, it's not going to happen like we might think it would, but when I click on that, it actually moved it right 3. So anytime that this is applied directly to the x, this transformation, it will happen backwards from what you would think. So if we subtract 4, it's going to move it right 4. So therefore, whenever we add functions or add values, add 1, add 2, or add 3, notice it moves it to the left. So again, this happens backwards from what we would think. And the way we're going to write that is, in order to move something to the left, we take our function, and inside with the x, we're going to, in order to move it left, we're going to add a number, add a value. So f of x plus h would move it to the left. So f of x minus h, if we take inside with that x and subtract a value, it would move it to the right. Okay, now let's take a look at reflections. First off, a reflection in the x-axis, or reflection across the x-axis, which, by the way, since we're reflecting across the x, this would be vertical. That's very important to understand. That's an up and down reflection. So going back to Desmos, let's take a look at this. If we have our parent function, y equals the absolute value of x, we know that's a v-shaped graph. To reflect it across the y, or across the x-axis, to reflect it vertically, make sure that we do not apply the negative, which a negative is what flips it. We do not apply the negative directly to the x, but notice where it's at. It's outside of the function again. When we put a negative outside of the function, it takes your original function and it flips it across that x-axis. So therefore, going back to our transformation sheet, a reflection across the x-axis would be a negative function, a negative f of x. We apply the negative in front of the function itself. Now, a reflection across the y-axis, again, this would be a horizontal because it's left to right. A horizontal reflection would be applied inside, because anytime we're doing anything horizontally, then that would mean that we're applying it directly to the x. So let's go back. And the reason I put two different functions here is because here, if I reflect this across the y-axis, if I reflect it horizontally, it's actually the same function back again. So let's take a look at this square root function, y equals the square root of x. If I go inside the function and I apply that negative, it reflects it across the y-axis. And again, notice from what we said a while ago, if I were to go outside of the function and apply the negative there, it would reflect it up and down or vertically. So therefore, to reflect a function horizontally, you take your x value and you make it negative. Okay, last up is your dilations, and a dilation is a compression or a stretch. First off, your vertical dilations. And remember, since it is vertical, we have to apply it on the outside. So when we're talking about our vertical dilations, we're multiplying or we're dividing. So here's how it works. If you multiply by a number on the outside bigger than 1, it's going to stretch it. And what I mean by stretch it, points that used to be here will now be, in this case, since I multiplied by 2, points that used to be here will now be 2 times as high. Point that used to be here is now twice as high. Okay, so you're taking every point, and it's kind of like you're stretching from this x-axis. It's twice as tall or twice as far away from the x-axis when you multiply by 2. So a vertical stretch is what that would be called. When you take your function and you multiply it by some a value, let's do a times f of x. But here's the thing about a would have to be greater than 1. In order to be a stretch, you have to have a value greater than 1. And let me put some absolute value bars around that, because if a is a negative value, then like a negative 2 or something like that, then it would still stretch it times 2, but it would also be a flip. So the absolute value, the value of that a value would have to be bigger than 1. Now, a compression would be our second type right here. If you take and you multiply by a number smaller than 1, or whose absolute value is smaller than 1, it's going to compress it. Like in this case, I multiplied by 2/3. And notice every point is now 2/3 of the way to the x-axis. What used to be at 2 is now at 4/3, which is 2/3 of it. What used to be at 1 right here is now at 2/3. Okay, so in order to compress, we're going to do the exact same thing. We're going to multiply your function by some a value. However, that a value would have to be less than 1, and we'll do the absolute value of a again. It would also have to be bigger than 0, so it has to be somewhere between, that a value is somewhere between 0 and 1. Now your horizontal dilations work a little bit different, and I remind you that when we're dealing with horizontal up here, when we're dealing with these functions horizontally, that it worked backwards. The plus h moved it left h, the minus h moved it right h. Now these work the exact same thing, they're going to be backwards. So the same way that over here we multiply to compress it by a number between 0 and 1 and multiply by a number bigger than 1 to stretch it, again, backwards. So let's go back and look at Desmos. If you have your square root function here, if inside you were to multiply the x, again, now that you see that it's inside with the x, you know something's going to happen horizontally. If you multiply by 2, it is now half of what it used to be. So what used to be here at 2 is now over here at 1. You see that? It's half closer, okay? What used to be at 4 would now be over here at 2. So it pulls it half as far away from that y-axis. It pulls it towards that y-axis half of what it used to be. And the same thing with, if you multiply by the 1/2, it makes it twice as far away. So what used to be here at 4 is now over here at 8. So it stretches it horizontally by the reciprocal. So multiplying by 2 on the x, reciprocate that, and you get 1/2. It's going to compress it by 1/2. Multiplying the x by 1/2, reciprocate that, you get 2/1 or 2, and it's going to stretch it times 2. So your horizontal stretches compressions will work in this way, and we'll use a different letter here. If you take your function and inside you multiply by x, your b value times x, it's only a compression. if your B value now, the absolute value, is greater than 1. Okay, it would compress it. If it's a number like 2, if it's a number like 3, because you got to reciprocate it. And write the opposite for a stretch. F of B times X, where you're multiplying the X times some B value, will only stretch it if that B value, the absolute value, is somewhere between 0 and 1. So therefore, in our vertical dilations, the function will compress or stretch vertically by a factor of A. And in this case, your function will compress or stretch horizontally by a factor of not B, but 1 over B. You have to reciprocate it. Okay, so what I'd like to do now is go through every one of those transformations for you and just real quick give you a reference sheet of what would happen. So I'm going to do that using the function y equals 2 to the x power, which is, here you see the exponential function. Again, if you add or subtract to the entire function, not to the x, if you add 3, it's going to take your original function, it's going to move it up 3 units. If you subtract 3, it doesn't change anything, it just moves it down 3. It's identical, it's just moved up or down 3. If you add or subtract to just the x value, if you add 3 to the x, it's going to move it left 3. If you subtract 3 from the x, it moves it right 3. If you put negatives on it, if you put a negative in front of your entire function, it's going to flip it across the x-axis up and down. If you put the negative on the x, it's going to flip it across the y-axis left and right. Then finally, multiplication. If you multiply your entire function, not the x, if you multiply the entire function by a number, it's going to stretch it. It's going to stretch it 3 times vertically, which means every point is 3 times taller or 3 times higher than it used to be. If you multiply by a third, then every point would be a third as tall as what it used to be. And then directly to the x, this reciprocates things. If you multiply your x by 3, then every point will be 1/3 closer to the y-axis. So even on both sides, it's going to pull it from the right side, it's going to pull it 1/3 of the way to the x-axis or the y-axis. And from the left side, it's going to pull it 1/3 of the way closer to the y-axis as well. And then when you multiply the x by 1/3, again, you reciprocate it. That's going to make it 3 times farther away. So what used to be at 1, 2 is now at 3, 2. So it makes it 3 times further away from the y-axis.